Okay, so now we've talked about ignition, lubrication, induction. Let's talk about exhaust. What do we do with the exhaust air as it goes out? Now, generally speaking, turbine engine exhaust is pretty straightforward. Basically, you're going to have an explosion, and it's going to go out the back of the tailpipe and make room for the next, like a wad of air coming in with fuel in it, just like with a recip engine. However, there are some considerations that we need to kind of go over, and we'll get into that. Right now, let's just talk about the theory and the components that make the turbine engine exhaust system.
Okay, so turbine engines have several different types of exhaust nozzles depending on the type of the engine that it is. For example, turbo shaft engines in helicopters have an exhaust nozzle that forms a divergent duct, taking the exhaust instead of going straight out the back, it channels it up over the engine and into the rotor blades or maybe to a 90-degree overboard, depending on the engine and the airframe that's configured. Now, that type of nozzle doesn't provide any thrust, and all engine power is being devoted to turning the rotors through the shaft and the bottom. All right, now what you're looking at here is a turbo fan engine. Turbo fans kind of fall into either ducted fans or unducted fans. So a ducted fan engine takes the fan's airflow and directs it through closed ducts along the engine. All right, then it flows into a common exhaust nozzle at the back end of it. Now the core exhaust flow and the fan flow mix and flow from the engine through the mixed nozzle. What you're looking at here is actually an unducted fan, which has two nozzles, one for the fan airflow and one for the core airflow. All right, now on these engines, the fan produces the vast majority of actual thrust. So these are your CFM 56s on your 737. This is your LEAP engines. These are your A10 engines. There's only like quote fighter jet that has a turbo fan engine in it. And the whole idea is that the fan itself is the primary provider of thrust. And so whenever we're talking about exhaust, the exhaust side of, or the exhaust component of your turbofan engines are really just there to just get the exhaust gone, just to get it out and push it on its merry way. The fan is what's actually blowing it. And you're using the turbine engine to turn a really big fan. If you look at our JT9s, those big fan blades that you'll take off on the front of the engine, that's the fan for the JT9. When you go around the back side of it and you look upwards, you'll see that there's a high bypass, is what they're called, high bypass turbofan engines. There's a big gap where that fan can push that air through, squeeze it down a little bit, and then shoot it out the back to produce the thrust that they need. And then there's a smaller area where there's the exhaust from the turbine itself actually comes out, and it's not pressurized or anything like that. It's just simply just trying to get the exhaust gone, out of the way, mix it with the ambient air, cool it off so it doesn't make too much noise, doesn't burn up the engine, and go on its merry way. Now, compare that with a turbojet engine where especially like a turbojet engine with afterburner, say like an F-16 or something, then all that's happening there is no fan or anything. It's just literally the exhaust is getting squeezed out the back end of it, and that's what's the producer of the thrust for the engine. Okay, your turbo props like this PT6 here, it's just basically there to get the exhaust away from the aircraft, to try to disperse with it, get it into the cool air, and get it gone without any soot or anything else. Getting it on the airframe best as possible. If you'll notice those that exhaust duct is tilted away from the engine to about 10-15 degrees, and that's the idea, is to try to, as the exhaust comes out and it's pressurized, it'll shoot out and get away from the airplane altogether. It doesn't produce any thrust or anything else like that. The turbine is there just for the simple reason of turning the prop, and that's it. Okay, so this is where the jet engine gets real fun when we start talking about exhaust nozzles. Now, we've talked about like the F-16 that just basically blows hot air out the back, and that's how it goes forward. We've talked about afterburners, how you throw extra gas in there, causing further expansion of that air due to the explosion and the heat, and that causes more thrust to go forward. And but we haven't really talked about the exhaust nozzle yet. So there's a couple different kinds. So we're first the convergent exhaust nozzle. So as exhaust gases exit this nozzle, towards the rear engine, they flow out the nozzle. Now the nozzle, it forms a convergent duct, and the gas velocity is increased by providing increased thrust. The restriction of the opening of the outlet of the exhaust nozzle is limited by two factors. If the nozzle's opening is too big, then thrust is being wasted. You're not optimized correctly. If it's too little, the flow is choked in the other components of the engine. So in other words, the exhaust nozzle acts like an orifice, the size of which determines the density and the velocity of the gases as they emerge from the engine. And that's critical to thrust performance. So adjusting that area of the exhaust nozzle changes both the engine performance and the exhaust gas temperature. And when the velocity of the exhaust gases at the nozzle opening becomes Mach 1, the flow passes only at this speed. It doesn't increase or decrease. Sufficient flow to maintain Mach 1 at the nozzle opening and have extra flow creates what's called a choked nozzle. The extra flow builds up pressure in the nozzle, and then sometimes it's called pressure thrust. A differential pressure differential in pressure exists between the inside of the nozzle and the ambient air. By multiplying this difference in pressure times the area of the nozzle opening, pressure thrust can be calculated. And many engines cannot develop pressure thrust because most of the energy is used for other things, like driving propellers, fans, or helicopter rotors. However, in a turbojet engine, that is not the case, and that is how they go so fast. Okay, another type of exhaust nozzle is the convergent divergent exhaust nozzle. So whenever the engine pressure ratio is high enough to produce exhaust gas velocities that might exceed Mach 1 at the engine exhaust nozzle, more thrust can be gained by using a convergent divergent type nozzle. Now, when a divergent duct is used in combination with a conventional exhaust duct, it's called a convergent divergent exhaust duct. The convergent divergent, or CD nozzle, the convergent section is designed to handle the gases while they remain subsonic and deliver the gases to the throat of the nozzle just as they attain sonic velocity. The divergent section handles gases, further increasing their velocity. After they emerge from the throat, they become supersonic. As the gases flow from the throat of the nozzle, it becomes supersonic and then passes into the divergent section of the nozzle. Since it is supersonic, it continues to increase in velocity, and this type of nozzle is generally used on very high-speed aerospace vehicles. Now, this before, not 10 years ago, this was like okay, look, if you're in the Air Force, or you're on some black project somewhere, this is relevant to you. Nowadays, things are changing. You have Boom Supersonic and all these other guys that are coming around, and they're starting to fly at supersonic speeds on the civilian side. You even have jet companies that are now offering supersonic private jets. And so this is going to become more and more of a thing as time goes forward. Okay, so the most extreme version of a turbine exhaust nozzle is going to be the aerospike engine. Now, this is a rocket, nozzle. So, take this, understand that about this. So, not necessarily an aircraft engine yet, but one that definitely kind of highlights the physics that goes into these nozzles. Now, at ground level, you're at sea level. You're at 14.7 pounds per square inch of air pressure on everything. That means that the exhaust for your rocket engine is going to be constrained by 14.7 pounds per square inch worth of pressure all around the cone. Okay, but as you go up, that air pressure starts to drop off. Well, most rocket engines are designed to be most efficient on the ground because that's where the most demand is placed on them. As they start to raise up, however, they then start to lose their thrust. So, for every unit of propellant that's burned, there's like a certain amount of actual thrust that's produced on the ground, and then that number is reduced significantly at altitude. So by the time it gets to 30, 40, 100,000 feet, there's just so much less air pressure that then the pressure of the exhaust nozzle just starts kind of going all over the place rather than being channeled behind the vehicle. Well, so the aerospike engine was a way to combat that. So on the ground, it's opened up really wide, and it uses the air pressure to squeeze that rocket cone, I guess, to get the vehicle off the ground. But as air pressure starts to drop off and that back blast starts to kind of fan out, the aerospike starts to squeeze in and try to maintain the most efficient shape of that exhaust at all possible, so that way it can get the most out of its thrust. The so what of it is that you don't have to carry near as much rocket fuel, because now whenever you get up to above the Kármán line, you can get so many more pounds of thrust for every unit of propellant that you take with you. Now there's a lot of reasons why that like these haven't been used. People cite complexity and all kinds of things, but for our purposes today, it's just to understand the way that the nozzle helps shape the exhaust and how that exhaust gets used.
Okay, so another unique aspect of turbine engines, which is kind of similar to your turboprops with beta mode, is that like jet engines can go backwards through the use of a thrust reverser. Effectively, that's just going to send all your exhaust gas, instead of going backwards, it's going to send it forward, causing the opposite effect to happen in flight. It's going to slow their airplane down. So let's talk about thrust reversers, and we'll kind of explore that.
Okay, so thrust reversers are really, really simple. Essentially, instead of having all the thrust going out the back end of the aircraft and pushing the airplane forward, you have cowls that close and open up these other ports that then push the thrust forward. That allows the aircraft to taxi backwards. Or most commonly, whenever you land, there's a weight on gear switch that has that then keys off the thrust reversers, which are already armed during the pre-landing checklist. And then whenever the weight on gear switch keys those thrust reversers, they automatically deploy, and then they auto brake the landing gear, allowing the landing roll to be significantly reduced, as opposed to just like letting the plane naturally roll out and then you slow down. Now, from a safety standpoint, I will tell you to be very, very cautious around these things on the ground. There's been many mechanics that have lost their arms to thrust reversers, because these things are hydraulically powered and they're extremely strong. They're made to withstand a lot of force being put on them, will turn around, and they have to fight the exhaust because there's a lot of pressure and stuff. So whenever you get your hand around there and someone deploys a thrust reverser, that's a bad deal. Now, it's easy to just kind of know that this thing it could potentially deploy. Is that if you hear the hydraulic pumps running, which very loud and noticeable sound on the ground, you know that those thrust reversers have power going to them, and just to stay away from them. And you should always be on comms with whoever's in the cockpit, so that way they're not running some sort of test while you're messing around with the engine, because that will absolutely get you in a bad spot.
Okay, lastly, this is something that's totally unique to jet engines, is noise suppression becomes like a serious concern. Recip engines and even turboprops, which can be loud, aren't nearly as loud as, say, that our Lear 25 cranking it up and taxiing around. Over the course of probably the 70s and the 80s, noise suppression became like this very, very big concern, because all of a sudden you started to get into the jet era. You started to see a lot of jets landing in populated areas, and you had things like the Concorde, which were literally blowing out windows in like grandma's house. And all of a sudden, like the FAA said, like, "Hey guys, we need a timeout. Like we can't just be excessively loud. We have to calm down." So let's talk about noise suppression. Let's talk about why a jet engine makes the noise that it makes, and then what we do to mitigate it.
Okay, so aircraft that are powered by gas turbine engines sometimes require noise suppression for the engine exhaust gases when operating from airports located in or near highly populated areas. This is 100% the Learjet story. So you can, when we start talking about these hush kits, you can go look at the Learjet and you'll understand. But several type of noise suppressors are used. A common type of noise suppressor is an integral airborne part of the aircraft engine installation on the engine exhaust nozzle. Engine noise comes from several sources on the engine: the fan or the compressor, and the air discharge from the core of the engine. There are three sources of noise involved in the operation of a gas turbine engine. One is the engine air intake and vibration from the engine housing that that are sources of some noise, but it's not really that loud. But the noise generated does not compare into the magnitude with that produced by the engine exhaust, which is what you're seeing here. That's that hot air coming out, mixing with the ambient air, causing all of that sort of turbulence. The noise produced by the engine exhaust is caused by a high degree of turbulence of high velocity jet stream moving through a relatively quiet atmosphere. For a distance of a few nozzle diameters down the jet stream by the engine, the velocity of the jet stream is high, and there's little mixing of the atmosphere with the jet stream. In this region, the turbulence within the high-speed jet stream is very fine-grained turbulence and produces relatively high-frequency noise. The noise is caused by violent, turbulent mixing of the exhaust gases with the atmosphere and is influenced by the shearing action caused by relative speeds between the velocity and the atmosphere. Further downstream, as the velocity of the jet stream slows down, the jet stream mixes with the atmosphere and turbulence of a coarser type begins. Compared with the noise from other portions of the jet stream, noise from this portion has a much lower frequency. As the energy of the jet stream is finally dissipated and the large turbulence swirls, a greater portion of the energy is converted into noise. The noise generated as the exhaust gases dissipate is a frequency near the low end of the audible range, making a low rumble. The lower frequency of the noise, the greater the distance the noise travels. This means the lower frequency noises reach an individual on the ground, and the greater volume of the high frequency noises, and hence are more objectionable. High frequency noise is weakened more rapidly than low frequency noise, both by distance and interference of buildings, terrains, atmosphere, all the things. A deep voice, low frequency foghorn, for example, may be heard much further than a shrill high frequency whistle, even though both may have the same overall volume decibels at their source. And this is the same, also true for light. Like a red lens, you can see further with like necessarily a blue light because of the wavelength difference, the frequency difference. Noise levels vary with the engine thrust and are proportional to the amount of work done by the engine on the air passes through it. So that's basically how things work. Essentially, like you're gonna have this hot air that comes out, mixes with cool air, causes a lot of turbulence, and that turbulence is what we hear as jet noise. Okay, so these are examples of noise suppressors that you can find on a jet engine. So, for instance, on the left-hand side is what we have on our Learjet. So both of these break up the single main jet exhaust stream into a number of smaller streams. This increases the total perimeter of the nozzle area and reduces the size of the airstream eddies created by the gases that are discharged into the open air. Although the total noise energy remains unchanged, the frequency is raised considerably. The size of the airstream eddies scales down at a linear rate with the size of the exhaust stream. This has two effects. One, the change in frequency may put some of the noise above the audibility range of the human ear, and two, high frequencies within the audible range, while perhaps more annoying, are more highly attenuated by atmospheric absorption than low frequencies. Thus, the fall off in intensity is greater and the noise level is less at any given distance from the aircraft. In the engine nacelle, the area between the engine and the cowl has an acoustic lining surrounding the engine. This noise-absorbing lining material converts acoustic energy into heat, and the linings normally consist of a porous skin supported by a honeycomb backing provided by a separation between the face sheet and the engine duct. For optimum suppression, the acoustic properties of the skin and the liner are carefully matched.